Okay, for people who are joining this live stream, we are looking at some incremental language development as we head into version 12.2 of Wolfram language. And first on our list today is the wonderful world of combinators. And actually, I think I have to run this in a different version here.
Okay.
Go ahead.
Yeah, the first thing is to look at the glyphs. And so, yes, Andy is here.
Are they in the product or are they not yet here?
They're not yet in the product, which is why there's a screenshot there right in the middle.
Okay.
These updates are not in, correct?
Can we simulate this? What is that thing? Do you know what that is? Is it close to bullet or is it something different?
It's bigger than bullet. So see that comparison there? So it's basically, I think it's small circle filled in, which is apparently smaller than filled small circle.
Correct.
Okay. Okay. My question is, what's it going to look like when it has parentheses mixed in with it? Okay. Because that's the case that we're going to see a lot. And I just want to simulate that. So we've got
Try it with bullet. That's probably close.
I know. But so what I've got to do is I'm just thinking about how to do it because
I guess if you take bullet and move it up one size in font size.
Yeah, right. But so let's see. I just want to say construct what am I doing here? I want to say groupings of random choice SK, comma 5 or something. No, 4. Let's say comma F arrow 2. Okay. So then this gives us, okay, let's do that. Then now I want to make F be this bullet thing. How do I make that an infix? Bullet isn't an infix.
No.
Okay, so what I want to say is infix form or something. Is that right?
It's just infix of, I think % comma bullet is what you want.
No, how does it? I want to turn every F into a bullet.
Yes, which I think would be infix of % comma the string bullet.
I don't understand that. How does it know to put that into the Fs? No, it's just going to. That's going to turn the top level list into that.
Oh.
Yeah. What I want to do is take this, and then I want to say this thing / dot F of X blank Y blank goes to infix of. Actually, I don't need to say. I just need to say X blank 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 like that. X colon this. I think goes to infix of that comma bullet. Right? Okay, and then I want to do this. Okay, so I want to say GGG, that is GGG / dot that. Oh no, what's happening? Oh God, no, I want to, how do I do that? I want to do, what I want to say is map. Gosh, this is remarkably hard to do. Map / that into this, onto GGG.
Here, Stephen, I have a locally built front end with the font. So if you want to just dictate to me and I share.
Okay, why don't you just, I'll just put this in the chat and you can run this.
Okay.
Except instead of F, I want application there, presumably.
Right.
Should you share your screen?
Yeah. Okay, so we have that guy. Now we change this to app If I could type. Why is did I misspell this or oh, does my kernel not have application? This no, but it has to have application. So how can it not?
Well, why don't you go?
All right, I'll stop sharing, and if I get this working, I'll let you know.
Okay, but that's what we have to do to test this is we have to get something with parentheses in it, because look, come on, somebody help me out here. We can do it with this. I want to map it. There we go. There we go. That did it. Okay, comments from combinatory aficionados.
There's too much white space. Other than that, I actually like this better than the larger one in the proposal.
Of just using the bullet. Well, so how do we reduce the white space? Do you think there's a way to do that, or?
I mean, that seems. I don't think there's that much white. I wonder if that's because of the.
Well, there we
infix
go.
creating.
That's a simulated white space reduction, and I agree that looks better.
Right, except I'm not sure how much of that white space is real and how much of it is just the sort of the.
No, I know the infixery.
Yes.
Right, so that's what has to be checked. Now the question is, if we made that bullet slightly bigger, by saying here, style. I don't know what we need to say here. Let's say 12 point or something. Let's say style 15 point. Is that making it bigger, or is it not making any difference? I'm very confused.
Okay, if you want me to share, I can show it to you live.
No, there we go. 15. It did work.
I rebuilt my kernel, and now I have it working.
Okay, fine. Okay, we'll look at it in just a second. Let's just see this, because I think we've got a good simulation here. I can't really tell the difference between those two sizes. I mean, but this looks pretty decent, I think. Roman, what do you think in terms of this?
Yes, I agree. And I mean, the designers will certainly tweak the size to and the spacing correctly, but this looks decent. Yes.
Itai, let's see your screen.
Okay. Okay. I don't know what happened to all my S's.
Yeah, those are, well, who cares? But I mean,
but yeah, I mean, I think it looks good, except maybe with the parentheses.
Well, yeah, but I think that they're too big. Those dots are too big. We should go down in size to more like the size we have here.
Okay.
This is what the screen capture is. Yeah.
Yeah, over here. This is fine, and that's the right spacing for it, and I think it'll be fine. Could you just, Itai, could you go to, is that your natural size for that window?
No, that's 200%. This is 100%.
Okay, I think the dots are too big. I think we want to go to the smaller dots, and then I think we're good.
Okay.
Okay. All right, you can unshare. Thank you. Okay. Okay. Next up.
What about two-way rule? Do you also want the two-way rule to be longer?
Right.
I'm good with that. I think that's fine.
Okay.
Okay, thanks.
Okay, wait a minute. Are you off because what are we doing with these? What are those things? Are they the bold of our usual font, or what are they?
Yes. And they're template boxes, so we can customize them however we want.
Okay. And in traditional form, they're serifed, but often aren't they rendered sans serif, bold sans serif?
That would be a question for not me. I mean,
that's a Combinator question.
Yes.
Roman.
Well, I mean, what I know is that what we tweaked is that they are upright and not italic. That's as far as I could find a consensus. But about the font, I really don't know. I mean, if everything else, if the variables are serif, then these should probably also be.
Well, except that they're often rendered sans serif. I mean, just out of curiosity, let's go to the master. Let's look at Mr. Schoenwinkel himself. Well, here they're both. Here they seem to be italic and the regular font. Okay, so
yes,
Schoenwinkel.
But that's not what survived for later on. I mean.
Right. I mean, let me look. I have a book here, Modern Combinator book. Yeah, well, what they're doing is sans serif bold. This is the Hindley and Selden book.
Then we should do the same.
I think so. I think that's the standard, sans serif bold. So I don't know whether we have a standard sans font that we pick for that. Guys?
I'd have to research that. I don't know off the top of my head.
Maybe Andy knows.
Andy?
The one that ships with Mathematica is serif, sans serif, yeah.
No.
Is that what you're asking?
What I'm asking is, if we're going to use a bold sans serif font in traditional form for these characters, what should we use? Right? I mean, what is the style specification that we should give to get a sans serif, to get what we need? Do you understand the question?
I guess I don't. Just using the normal bold sans serif, is that not?
He does not. He does not. He doesn't. Yeah, this is a question for John. Let me. No.
I'm asking this. I'm asking, what do I do to make this sans serif? Do I say font family? If I give a font family that's a specific font family, Al Nile font family, that's not the right thing. What is our generic way of specifying sans serif? You understand what I'm saying?
That is, you put source sans serif or source sans would be what we ship.
No. I'm talking about, okay, that is a platform specific thing, right? I'm asking, is there a generic way to specify sans independent of the particular font on a particular platform?
Oh, sorry.
Yes, that's what I was saying.
Sorry. No, not that I know of.
Okay, that's possibly something we should have.
Right,
Sorry,
which is why I said this is a question for John.
Okay, all right, fine.
Correct. Yeah.
Okay. All right, so these are the named combinators that we have. Is that correct? And they have predefined definitions somewhere or not?
Well, there are no definitions. I mean, they have entries in the axiomatic theory. But I mean, what's there to define? You cannot just blindly reduce them, right? So.
No, I mean, the question is whether we have a combinator evaluate, which basically just does.
No, not.
Wasn't that? I believe that was intended for the function repository.
Yes, I mean, what my understanding was that we put the minimum required for proper support of the notation and the application into 12.2, and we have function repository for the algorithms for now. And then we'll have something more complete.
All right, okay.
I don't think.
So, I mean, my question is, okay, so this is for Mano, who's writing some of these function repository things. You should support both lowercase s, lowercase k, and these combinator s, combinator k things.
Okay.
Okay. I'm not sure what I'm going to use in my post about this stuff yet. I mean, I would like to use these, but I'm not completely sure. I need to get used to them. And also, it depends on when version 12.2 ships relative to that, and so on. Okay.
So there's one question that we haven't talked about is whether we should support some short input forms for these, because they are kind of long to type.
Yeah, they are.
Yeah, well, they're not that long, right? There's CO and then autocomplete.
Well, but there are too many for the autocompletion.
I
they don't all.
suppose.
They
By the
don't
way,
all
in the
show up.
autocomplete ranking, you should put SKI first. Right, and when you specify autocomplete ranking,
Yeah, we can do that. But I agree the escape sequences will be good so that the input is short, so that we can
yeah.
directly.
Right. Well, then let's say escape. Lowercase c, capital S. I don't think we're going to use that for anything else.
Right.
Okay.
Mm-hmm.
All right. Onward.
Okay, so here we have now a discussion on what axiomatic theory and final equational proof should do. And the discussion is that, and this is for Jonathan to comment, it seems that the general case requires an extension so that the theory is high order. But that makes the computations very slow because we need the non-purely equational case.
Right. So that is a problem, and that's not really one that can be resolved, right? My find combinator proof function has some optimizations that gets around that issue, but the basic issue is that I think Stephen and I were discussing this yesterday. So there are various subtleties that occur when you attempt to make combinatory logic into an algebraic theory, and one of them is that if you just do it naively, unlike in all other algebraic theories, there is a distinction between intentional and extensional equality. For exactly this reason, what you need to do is, if you want to be able to support proving over both cases, which is what I think you do need an additional, essentially an extensional equality axiom, which I guess is what you're doing here. It is possible to optimize, but ultimately that we do need something like that.
So this is the additional axioms.
Correct.
Gosh. So it has an actual implication function in there.
Right. And I think that's the problem. That it's that implication that it's not easily, cannot be supported in purely equational case.
Right. I mean, first order theorem proving with find equational proof is significantly slower than equational theorem proving.
Right. But the pity is that many of the interesting theorems can be solved already in the equational case. So perhaps here we should have just two collections of combinator axioms.
I agree, but we should make it clear that one of them is proving extensional and one of them is proving intensional equality.
Okay, tell me a practical reason why one cares.
What do you mean?
Because what's a theorem that you can't prove in one? Go ahead.
You don't want to prove theorems that are wrong. That's the practical reason.
Okay, but what type of theorem? Okay, so again, so I agree with you. We're going to need two sets of combinator axioms. But what is an example of a theorem that you can prove if I removed all these equality axioms here?
Okay, so I mean, obviously the trivial textbook example, I mean, the one that's in all the textbooks is SKK and I, right? That would be an example.
What you mean, S of S?
Yes. Go down to the examples, you will see it.
Okay.
It's right there.
So SKK and I are extensionally equal, but not intentionally equal.
Because basically you have to add a leg to the thing to show the equality. Is that right?
Sort of, yeah. I mean, the point is that they're not in the strict if you compute the strict deductive closure of the combinatory axioms as an abstract rewriting system, SKK equals I is not a theorem in that deductive closure. But it's still the case that extensionally, XKK of X equals I of X for all X.
I understand. In other words, the thing doesn't evaluate unless you put another tentacle, unless you add that argument to it.
Right. Yeah. And the general reason why that happens is because, I mean, the thing we discussed yesterday, the fact that there isn't a notion of lambda binding. So you have a fixed number of things that you eat.
I don't know how to read this. Dane, I think on our live stream says, those axioms look ugly. Schoenfinkel will be disappointed looking at those variables. Yeah, there's something to that. It is a bit disappointing that a variableless axiom system has to have variables in it. How does one do that? There must be a way of doing combinatory reduction that mentions no variables.
Yes, there is. That's the nominal logic I was telling you about yesterday.
See, the problem, Jonathan, is that you always have to tell me about things at least 3 times for me to actually understand them. I didn't understand the nominal logic thing. What is the idea? So the idea is...
So nominal logic... okay, so there's actually... I forget when our logic programming meeting is meant to be, but this might relate to the stuff we discussed there. There are some systems... There's a theorem proving system called alpha lean TAP that's based on this alpha logic, where basically you take first order logic and then you mod out by alpha equivalence.
Right. Okay. Which is this variable naming thing.
Right. So in the theorem proving, well, in the mathematical logic literature, these are called grounded terms or grounded expressions, right? Ones that don't contain any free variables. You're just reasoning purely over the syntactical structure.
Sorry, what are they called?
They're called grounded terms or grounded formulas.
Okay, grounded formulas have no free variables, you're saying.
Right. So in effect, when you do theorem proving over nominal logic, you're proving over the set of grounded formulas.
Okay.
And so what? So and that becomes relevant in the combinatory logic case because the proving of intentional equality is a proof of combinator expressions as considered as grounded formulas, whereas the extensional equality is the proving of them as considered full, algebraic equalities.
So is there an axiom system where you just look at a whole SKK blah 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 thing and you just do substitution on that?
Of course. But that's the intentional, that's only going to show you intentional equality unless you give it.
Okay, so intentional equality is the pure pure SK, etc. Without, so basically what the main point you're making is that S of K, by the way, we're hearing some typing there, S of K of X, if I say SK, SK fixed point evolve. Oh, I don't have it evaluated here. Let's see, I'll pull this up. Hold on one second. Let's see. Okay, here we go. Okay, so you're saying this thing here. So these are my fixed point things. By the way, question for Roman, which you might know, is if I'm doing leftmost outermost, is this the right way to guarantee to get leftmost outermost ordering? Is to say first of the sort by the position.
Yeah, I would have to look at this some more, but we clearly need this at some point in the language. But,
what?
Well, these reduction strategies, so you don't have to do things like this, right?
Right. But right. Okay. In any case, SK fixed point evolve of this gives that. Dandy. Okay. So now just applying the combinator, nothing's going to happen to SKK, right? Because what you're saying is for all X, SKK of X equals I of X, right?
Right. And so in a universal algebraic structure, intentional and extensional equality are the same, which is how theorem proving works. The tricky thing with lambda calculus and with combinatory logic in particular is that they're not equivalent. For this reason.
In what sense? Okay, so hold on. The reason they're not equivalent is because there essentially are rules that don't apply. It's not something where you can do.
Right.
There's no algebraic substitution that you can do. It's just, sorry, the rule doesn't apply.
Right. And so this is, again, as I think as I may have mentioned yesterday, that when you do the naive translation from of lambda calculus or combinatory logic into an algebraic theory, one key axiom of the lambda calculus, which is this xi rule, doesn't hold.
Yeah.
That's basically the extension out. That's the extensional axiom, essentially. the external equality. And the reason you get that subtlety essentially is because you don't have lambda binding in combinators.
Right, but so here, there are things we can prove that don't have to have variables hanging out. So we should say, what should we call them? Combinator algebraic axioms and just combinator axioms, or what? Or combinator nominal axioms? Would that make sense if we call them combinator nominal axioms? And those are the ones that just have the S and K stuff in them. And combinator equational axiom. Does that make any sense? Jonathan, others? Jonathan, can you comment? Hello.
So something I'm confused about is that the SKK equal I can be proved with a simpler case, right?
I think it needs these things, doesn't it? Jonathan, are you still there?
No, I mean, Roman has the example there, what he calls the proof SKK equal 1. So,
yeah, but I mean, these are the cases where you stick in the variables and then you just do naive reduction, right? I think.
Exactly, but
if it works, it's great. But if you stumble upon the fixed combinator, then it usually doesn't work.
No, but you've got something with an X here. So we know it works with an X. The question is whether SKK on its own works.
Well, not.
Is Jonathan still here, or did Jonathan leave?
Sorry, my audio dropped, but I'm back now.
Okay, fine.
What's going on?
Okay, so my suggestion is that something like that these would get called combinator nominal axioms, these get called combinator equational axioms. Is that stupid?
That's not stupid. I think, yep, that looks okay. The name
is these are a little bit unequational. I mean, because these are two-way. I don't think it should be two-way. It should be two-way rule, not left-right arrow, shouldn't it? Because two-way rule has a fighting chance of being usable for something else. Left-right arrow is purely syntactic.
Right, and it has a nicer escape form, etc.
Right.
Also, because they're not strictly equational, because they are first-order propositions, should we call them intentional and extensional, or do you think we should stick with nominal and equational?
I think I will never be able to remember which one is intentional, which one's extensional.
Okay.
And I can't remember even right now which one is. But is it the case? Okay, so the simpler axioms could not prove this if I left off. In other words, if I left off the X here and I just said equals I here,
yes,
then we should be able to prove that, right?
Yes, but only with ones that only with axioms that take extensional equality into account.
Okay, but isn't that what this does?
But then you shouldn't use an equals, right?
I see. So this would be left, right arrow.
Whereas, I mean, here's a trivial example of something that is intentionally true.
Which one is intentional? Which one is extensional? I can't remember. Which one is which again?
So when we use equal, Jonathan, which one it is?
Sorry, something keeps happening with my audio. Sorry, so extensional is the one that's, where you're introducing arguments from outside. Intentional is where you're just proving things over the structure.
Okay.
But what's the relation of that with having the additional x's?
So the additional x's is the intentional case.
But above, we still have the x.
Now you're confused.
Yeah.
Hopeless. Okay. Okay.
Both of those lists have the additional x's, and they can prove different things.
Right, but the x's in the simple combinator axioms, those x's are just you know, in some sense, you can think of them as being like syntactical X's. They're just saying anything including a variable or a combinator could appear here. Whereas the X's in some of the X's in the full combinator axioms are acting as variables, not as combinators. I know that distinction doesn't really exist, but
yeah, it's even more complicated. That's a typed version of this.
But I thought the problem here is that we want to use application. And application in the end has to apply to something. So you need this additional X. Isn't that the case?
No, the whole point is that SKK is equal to I in some abstract sense. It's like saying these two functions are equal without saying functions are equal at you know, with specific argument, this, that, and the other.
Mm-hmm.
Okay, why isn't this working?
Well, I think it's just slow. This is what we were discussing before. But if you try
it's so slow. What's that? No, I understand. The other way of doing it will work just fine. But the other way of doing it has an equal sign here. Is that really a justified equal sign? And why are these things not equal signs up here? Jonathan, still with us?
Yes. So, I mean, I didn't produce this axiomatization, but I would assume they're not equal signs because you need, when doing theorem proving over first order logic, the equal sign gets used in the equationalization. So your first order axioms can't contain equal signs. The prover for mixed, sorry, please.
Basically, Jonathan gave us a list of extra axioms that need to be added for application. And so part of that was using a formal equal instead of, you know, the built-in one.
Basically, find equational proof doesn't yet support mixtures of first order and equational logic. If you want to do that, you have to define your own sort of equality predicate. It either does pure equational or pure first order, not a kind of hybrid.
Is that a permanent thing or is that a temporary thing?
It's a temporary thing in the sense that I can fix it, but it will take effort.
Boy, this is complicated. I mean, unfortunately, what we're dealing with here is, you know, different shaped pegs, so to speak. Boy, it's difficult. Look, I think we're not going to have a perfect solution for this version. And the only question is we've got, you know.
Yes, I mean, I would strongly suggest that we at least support those what are here called simple ones, because that's the kind of simple examples that everyone does. Understanding that they are not good enough for everything.
I agree. So actually, I think in the spirit of what Roman was saying before about having minimal functionality in system and then exposing everything else to the function repository. So because the new version of Find Combinator proof does support both extensional and intentional proving with options, what we could do is just include simple combinator axioms in axiomatic theory and then document it to say Find equational proof by default only does extensional proving, but then have Find a combinator proof in the function repository that can do both.
So in other words, we'd support this form here.
Yeah, exactly.
So maybe we support that form and call it something like combinator nominal axioms or something. Is that even correct? Or do we just call it combinator axioms?
I think we could just call them combinator axioms.
Okay. All right, fine.
I mean, it's just the problem is not, okay, this is what I'm going to say. What I'm about to say is going to sound a little bit obscure. The problem is not whether the things you're describing are combinators or not. It's what the meaning of the equal sign is, right?
Yeah, I understand.
But as long as we make it clear in the documentation that that equal sign means intentional equality, then we're okay. Sorry, it means extensional equality, I should say.
I love it. We're just totally confused here. Dane is commenting on our live stream, so it's not really find equational proof, but find extensional proof.
That's a good point. I mean, because in ordinary logic, the axiom of extensionality says that you can, I mean, in effect, this is what univalence is, right? Univalence is saying, the univalence axiom is saying you can convert between equality and extensionality. In other words, that if things are, things are algebraically equal, then you can treat them as being identical. What we're encountering here is the well-known fact of combinatory logic that it's not a univalent theory.
What do you mean by that?
So so the univalence axiom extends this notion of propositional extensionality to type theory, right? So it says that if I, essentially it's telling me that if two types are sort of equal, then I can treat them as being identical.
Yep.
And, sort of constructive theories based on homotopy type theory and so on all obey the univalence axiom. Combinatory logic, if you naively axiomatize it, is not a univalent theory, precisely for this reason, because essentially algebraic equality doesn't imply, algebraic equality and structural equality are not the same thing.
What the heck is algebraic equality in a combinator?
Well, that's the extensional case.
I see, where you've added enough variables to saturate the thing, and so
Right.
then it can do its thing. Whereas if you don't give it enough variables, it can't necessarily decide that answer.
So SKKX, because it's saturated, you can write a multiplication table with S and K be with the application operator being your binary operation, S and K being constants and X being a quantified variable. But with just SKK, you can't write that multiplication table. There's no sort of algebraic way of reasoning about that. You have to do it structurally.
Right. Right. Did you, by the way, do you know if there's a finite model for application in the case where for combinators? Does anybody know that?
There's a model. There's this thing called it's due to a guy called Plotkin, which is a finite model for the lambda calculus, which you can sort of trivially convert to a finite model for combinators.
What does it actually look like? Anybody know? I mean, I just wondered whether I've just never seen its explicit form. Roman, have you ever seen its explicit form?
No, I was very surprised to learn that there should be a finite model, so that's not something I've ever encountered.
Interesting. Well, Mr. Plotkin has papers about a wow, it's kind of interesting.
Did you find his graph model?
I found his his thing about chemical systems.
Nice.
He's onto the same shtick as we are. Yeah, realizing that calculus of communicating systems is related to biochemical events. Good for him. Where is inf.ed.ac.uk? Who knows?
That's the Edinburgh University Informatics Department.
Oh, okay. As opposed to infirmary. Okay. Okay.
They have a logic group.
Oh, okay. That must be what this is. Fascinating. Okay. Okay, so now what are these other things here? So this is
I think this is just another example in preparation for the documentation.
I mean, I'm collecting examples because I'm probably supposed to write the first draft of the web pages for these things.
okay.
And so the other one, this one is a kind of larger and ugly one, but just want to show. This does combinator reduction, and it detects cycles and it stops if it goes too much or there's too many. And so I take combinator expressions, apply some variables, and then see which ones end up as ground terms.
What is a ground term?
one that no longer contains s and k, so it just contains the variable that you stick in. So here I generate all s and k expressions with up to 4 literals, and then I see which ones reduce, and so you'll find all the expressions that are equal to I. So you find skk, sks further down, but also, of course, longer ones.
Right, but I mean, you can also do reductions that don't have the x at the end.
Yes, but then I mean that would be a different search criterion, right?
Yeah,
Then the only probably the most meaningful stop would be when it no longer changes.
Right.
So here I only return those cases where all the s's and k's are gone. But that's a simple change.
Yes. Okay. Well, looks reasonable enough. All right, let's look at this non-binary application.
I think this is completely misguided and wrong.
Well, let's see. So the idea here is to allow application to take from one or more arguments to simplify inputs. Because in the same way that you may want to write...
right, but you don't we don't allow rule of ABC as a shorthand for A goes to B goes to C.
Do we allow it for composition?
No. Well, composition is flat. It's not a binary operator. Either it's a binary operator or it's not.
Wait a minute. What composition here of this, right? Oops.
Yeah, so composition is not a good precedent here. It would be more like compose. Compose did, I think I have a comment at the very end.
We gave up on compose.
And compose also didn't have an operator.
Yes, but
look, either it's a binary operator or it's not. If it's not a binary operator, then I don't know why we've invented it. And if it is a binary operator, then it doesn't magically turn itself into some other form.
No, it's the other way around. I mean, if you want to input a long list of left associative terms like A apply to B, C, D, and so on, then it's very easy to enter it without these parentheses. But if you want to actually, say, convert a list of these into an application, then you would have to do the grouping and the left associativity by yourself. And so what this does, if application has more than 2 arguments, it will automatically turn itself into the binary form. So it merely makes entry of expressions simpler.
No, how does it make entry of expressions easier? You do F escapes, AP escape, G escape, AP escape.
Whatever.
No,
listen,
you say list of A, B, C, D, and then you say apply application to list.
Right. It's more a programmatic thing. Of course, we have the operator, as you say, for the input, right? For the interactive.
Otherwise,
system.
you have to fold it in, right? Otherwise, what you're doing is saying fold
exactly.
application onto that list.
Mm-hmm.
Okay.
Is that the right way around? Is that a correct direction of folding?
I think it's not. I think it's.
Yeah, it is.
I think it has to be fold right. No, this is fold left.
Yeah, it is left associative. That is correct.
So you just say fold application onto that list.
Yeah,
right.
You could do that. Yes. Okay. So
I think we should not make application have a more than binary form. Okay, but I think we should document the fact that you can fold like that.
Oh, yeah, I mean that's actually a good example for the documentation. Yes, obviously. Yes.
Absolutely not. That will just blow up any other use of application.
Right.
Yes, so I think we agree on that one. I mean, it was more an exercise of trying to find the correct limiting case, but nobody will ever. It will never happen in the wild, right? There will never be an application with no arguments occurring naturally. So
that's cool. The fact you can say application arrow construct and it turns into that form.
And
Yes, I mean,
construct goes to application is that second thing you give there, right?
yes, and that is unfortunately not possible because construct is not really an operator once it's there, right? But I think it's nice enough that you can use the @ sign and the future filled circle on the right-hand side.
Right, and these look like fantastic properties and relations examples for the ref page.
Yes, of course.
Yes.
That's why I came up with them.
Right. All right. Well, this looks good.
So is that good for 12.2?
I think so. I think we're good.
Very good. Very good. So we'll probably need a short docs meeting at some point for the ref pages.
Yes, I'm happy to do that.
Mhm.
And I mean, I'm currently, actively working on doing stuff with Combinators, so that will hopefully shake down any further issues with this.
Okay.
I must say these things are so bizarre, just so bizarre. It's just like complete alien set of concepts, particularly for their time. I mean, I'm just, anyway, very surprising. Look, I don't think we're going to get to this this major function repository thing. So I think we should wrap up here. And people following live streams, we actually have another one in 30 minutes about biosequences.
And I'll be there, so I'll see you in half an hour.
Oh, you're going to be there. Oh, nice. What are you doing with biosequences? That makes me suspicious.
Well, I've been trying to train the scientific computing people how to write proper documentation, but I was involved because it's touching all of the string pages.
Manipulation function. Yeah. Right. Okay. Forward to seeing you there. Thank you all very much.